In this lesson, we will learn about the basics of computer animation. To begin, we should learn a little about traditional animation techniques. Now, before computers, animators had to hand draw every single picture, and then record them with a camera. The resulting film looked like a moving picture when played back. Now, these images are called frames, and a frame is simply an image of a frozen moment in time. We also use frames in computer animation because they're the smallest visible unit of time in the animation. The traditional method of animating is time-consuming, but hand drawing gives you precise control over every frame in your animation. The advent of computers introduced a faster way to animate, with the computer generating each frame for us. Instead of drawing every frame, you create objects in an animation program and animate them using computer-assisted tools. This is faster because once you've created a character in the computer, you don't have to redraw it every frame. And because the computer does a lot of the work for you, complex animations are much easier to create. In this lesson, we will learn about 3D space and how the computer keeps track of an object. An understanding of 3D space, or three-dimensional space, is important to 3D animation because, well, they're both in 3D. Well, what does that mean? Without getting into a boring and complicated mathematical definition, each dimension describes one part of an object's position as a number. Now, these numbers are stored in an object's attributes. And attributes can store anything from an object's name to its current location. Let's start with the simplest example, animating in one dimension. This restricts our object to moving only along a flat line, and this is very limiting. So let's add a second dimension. Now, by doing this, we can now move up and down as well as left and right. Finally, we'll add the third dimension, and now our object can move anywhere. Now, this may seem confusing, but it will quickly become second nature to think like this, because we live in a 3D space. If we pick up the ball, we can move it left, right, up, down, towards us, and away from us. But there's a problem with saying we can move it left and right, because what if our view changes? What was left a second ago is now right. Luckily, mathematicians have given us a handy guide to describing 3D space by breaking the three dimensions into three axes. Let's move our view back to where we started. Now if we move the object left and right, we can say we are moving it on the x-axis. Moving it up and down is the y-axis. You can probably guess what the third axis is called. It's the z-axis. Notice that the x-axis can no longer be described as left and right, but if you say move positive in the x-axis, it's easy to know where it will go. In this lesson, we learned about 3D space, the three different axes, and how the computer tracks our objects using values. In the next lesson, we will learn different ways to manipulate objects in 3D space. In this lesson, we will learn the three primary ways to manipulate a 3D object. This is called transforms. The first way we've already seen, which is translate. When we move an object around in 3D space, we are translating it. In other words, moving it from one position to another. To activate translate mode, we can either use a keyboard shortcut or click a button in the user interface. A translate manipulator, which has three arrows that correspond to the three axes, each of these point in the positive direction of those axes. The x-axis is red, the y-axis is green, and the z-axis is blue. The next manipulator we're going to look at is rotate. When we activate rotate mode, you'll notice that our manipulator changed. We now have rings around our object. When we grab the red ring and drag, the object now rotates around the x-axis. The last manipulator is scale, which changes the size of the object. As you can see, the manipulator changes yet again, giving us visual cue on how it will behave. We can scale in the individual axes, elongating or squishing the object. We can also scale the object in all three axes at once by modifying the center of the manipulator, making the object grow or shrink proportionally. Let's use what we just learned to animate a door opening and closing. We'll start by adding some rotation to the y-axis. Because the pivot point is in the center of the door, it rotates around that position. To fix this, let's activate the Move Pivot mode. This allows us to move the pivot point to where we want the rotation to take place. Now, by translating the pivot point to the edge of the door, we can now animate the door opening and closing and not just spinning. In this lesson, we learned about the three manipulators: translate, rotate, and scale, and about pivots. In the next lesson, we'll learn how to control time. In this lesson, we will learn how to control time. This ability is just as important as knowing about 3D space because an animation is moving an object through space and time. In computer animation, time is defined in frames. So how many frames are in 1 second? Well, two common settings are 24 frames per second, also called FPS, and 30 frames per second. For this training, we'll be using 30 frames per second. This is called the frame rate. Now, depending on what medium the animation is for, say TV versus cinema, you might need to change the frame rate. And make sure you set the frame rate before animating, because it is a headache to change after you start animating. Now that we know the frame rate, we can begin moving through time using a panel called the time slider. On the time slider is a marker that you can use to set the current time or frame. The frames are represented by tick marks and numbers on the time slider. Underneath the time slider is something called the range slider. Using this, we can limit the number of frames visible in our time slider, thus focusing on only a small portion of the animation. Another way to watch our animation is by dragging the marker across the time slider. Now, this is called scrubbing, and it's a good way to get a feel of how our animation is looking. The only thing is, it's difficult to see what the animation will look like because the time moves just as fast as the marker moves, not at the frame rate that we specified. Similar to a remote control, we can simply press the play button to tell our computer to play our animation back. This is found in the Playback Controls panel. This panel can do many things beyond a regular remote, such as play the animation backwards or move one frame at a time, as well as go to the beginning or end of the time slider. But even using this panel is not a foolproof way of previewing our animation at the right frame rate. Depending on how complex the animation is, the computer still might play the animation back at the wrong speed. Fortunately, there is a third option for watching your animation, and that's to make a preview. Now, this tells the computer to evaluate every frame, create an image for it, and then output that as a video which plays at the correct frame rate. In this lesson, we learned about frame rate, the time slider, the range slider, and previewing. Now, in the next lesson, we'll take a look at keyframing. In this lesson, we're going to learn about keyframes, the building blocks of animation. Alright, so far you know how to move an object around and change the time. So let's try setting up an animation. Here we have our character on the left side of the screen at frame 1. Let's move to frame 30 and move that character to the right side of the screen. Now when we play this back, we should see him move from left to right. But what happens is that the character just stays where it is. The computer doesn't remember where he was at frame 1 because we never told the computer to remember that position. To create an animation, the computer needs to mark what changes we've made to our objects, and we can do that by setting a keyframe. Computer animation is nothing more than attributes changing over time. To track those attributes, we have to set a keyframe to tell the computer that we want our object to be here at this time. Think of a keyframe like a box that holds the value of an attribute on that particular frame. You need at least 2 keyframes with different stored values to create an animation because the computer needs a change in an attribute to animate. To set a keyframe, we can click the key button. So if we move the time back to frame 1 and move the character to -5 on the x-axis, we can set a keyframe. The computer now knows that he is at -5 on frame 1. Now let's change the time over to frame 60, move our character to +5 on the x-axis, and we'll set another keyframe. Now when we play back, we have an animation. The character moves smoothly from -5x to +5x. You'll notice that when we set a keyframe, this little box appears on our time slider. These are keyframes, and we can edit them on the time slider. You can see our current animation takes about 2 seconds, but what if we want to speed it up? Well, we can just select the keyframe on the time slider and drag it to frame 30. Now when we play the animation, it happens in 1 second instead of 2. This way of setting keyframes is okay for a simple animation like this, but when we start to animate dozens of things on our screen, we're going to have to save time wherever we can. Now we can cut out the step of actually clicking the Set Key button by turning on Auto Key. Now what Auto Key does is it sets a key on the current time whenever we change an object's keyable attribute. This can be a double-edged sword because if you don't change the time, you would just be overriding the same key over and over again. But with a little practice, Auto Key can help you animate much more efficiently. Let's quickly recreate our example. So we'll turn on Auto Key and set the first keyframe on frame 1. Now, all we do is change the time to frame 60 and move the object. There, we have our animation. In this lesson, we learned about keyframes, the building blocks of animation, and how to use Auto Key to animate faster. In the next lesson, we'll learn about the dope sheet. In this lesson, we will learn about the dope sheet. Now from the previous lesson, we know how to set keyframes and move them around in the time slider. Editing keyframes in the time slider is great if you're doing small changes on a simple animation. But let's look at an example of a more complicated animation. Here we have our object falling and hitting the ground. We have a problem when it hits the ground though. It continues moving far too long. Now this is because our rotation keys are not on the right frame. So let's try fixing this using the time slider. First, we'll try to find the correct keyframe, then drag it to the left and play back the animation. Now that change just made the fall happen a little faster, but we still have the same problem. We can't fix this problem using just the time slider. We need another way to edit the keys. We'll use the dope sheet. The dope sheet is like a larger time slider that breaks the animation down into easy to see and manage parts. On the bottom are frame numbers, on the left are individual attributes from our object, and on the right are the keyframes. Now each box represents one frame. This gives us precise control of the timing of our animation. To fix the timing, we can just grab the rotation keyframes, shown as the filled-in boxes, and drag them over to the left. Now, when we play back the animation, the object drops, moves a little, then comes to a rest. Now this looks good, but let's add some drama to this animation by having it move in slow motion. We can easily do this in the dope sheet by just grabbing the last group of keyframes and moving them to the right. Now this prolongs the fall. Let's look at the final edited animation. We begin with a dramatic slow fall, then return to normal speed when the object hits the ground. So as we saw, the dope sheet is a great way to quickly edit the timing of either a large number of keyframes or keyframes of individual attributes. In this lesson, we will learn about the graph editor. So far, we've edited keyframes using the time slider and the dope sheet. But what's happening between the keyframes? Well, the computer is interpolating between the keyframes, or in other words, filling in the blanks. We can see the result of interpolation when we play an animation because the computer does it automatically. Interpolation isn't visible in the time slider or the dope sheet, but you can see it in the graph editor. Here we have an animation of an object dropping and hitting the ground. Now there are quite a few keyframes as you can see in the time slider, but let's examine this animation in the graph editor. Now we can see all of the keyframes and their interpolation, but it looks like a gigantic mess. Let's restrict our view to just a single part of the animation, the drop. Without all of these curves, there we go, that's much better. In the graph editor, we have the familiar frame numbers at the bottom, the various attribute names on the left, but what are the numbers in the middle? Well, this group of numbers actually corresponds to the value of the attributes. Now clicking on the attribute's name just shows those keyframes, so let's focus on Translate Y. We can edit a key's timing just by dragging it left or right, but we can also edit its stored value by moving it up and down. Now be careful though, because while you're editing the values, you might accidentally change what frame it's on, or vice versa. Now that we know how to edit keyframes in the graph editor, let's bring back all those curves. These curves, called the function curves or F curves, are a visual representation of the interpolation between the keyframes, and are color-coded just like the axes. They are drawn by the computer based on the value, frame, and interpolation type of each keyframe. Now that we know how the graph editor works, we can learn how to read each F-curve. Our object falls straight down, but in the graph editor, it looks like it's moving forward and down. Now, this is a very important thing to understand about the graph editor. The motion of the F-curve in the graph editor is not a direct representation of the animation. Instead, it describes how the attribute changes over time. So in the case of our translate Y F-curve, what the graph editor shows us is that our object is moving down in space and forward in time. We will learn how to edit and use tangent handles. So far, we know that keyframes hold values. What about the interpolation between the keyframes? That is controlled by the keyframe's tangents. A tangent is simply a line that defines the direction of the interpolation when it enters and exits a keyframe. We can edit these tangents using their handles to change the motion in between frames. Let's look at an example of a bouncing ball. There is a key in the air at the beginning and at the end of the timeline, and a key on the ground in the middle of the timeline. Okay, let's play it back, and it doesn't look like a bouncing ball. It looks like a ball floating to the ground and then floating back into the air. This is because the interpolation type is set to flat, which makes the motion move at a steady pace. Let's try editing the tangents to fix our animation. First, we'll grab the tangent handle, then drag it up. Let's play back the animation. Well, it's falling faster, but now it moves down too far and the motion is still too smooth. If we grab the other end and try to fix it, nope, that just does the same thing in reverse. To fix this, we have to break the tangents. Breaking the tangents lets us move each handle independently. If we drag the tangent handles into a V shape, our ball now has a sharp transition moving into the keyframe and out of the keyframe. The ball now falls quickly, hits the ground, and then bounces back up into the air. While you might be animating more complicated things, keyframes and tangents make up the backbone of computer animation. Tweaking tangent handles is normally the final step in editing the animation. The following lessons will deal with animating efficiently and ways to create complex animation. In this lesson, we will learn about ghosting and the various interpolation types. Let's take a look at our falling animation. Alright, so far we've seen the animation in the time slider, the dope sheet, and the graph editor. But none of them give us an easy to see, clear view of our animation. We have to play it, tweak it, and play it again to see if the tweak fixed the problem, and then go back to tweaking. It's not a very fast way to animate. Well, there is one last way to see our animation, and that's with ghosting. When we turn on ghosting, we see that we have a lot more dolls in our scene. Well, these aren't real dolls, but rather glimpses of where the object is in time. Now if we move a keyframe, we get instantaneous visual feedback. Ghosting is very useful for viewing the animation around the current time to see how your changes will affect the animation. Let's now use ghosting to look at the various interpolation types. Here we see our original animation on the left, and the animation with interpolation type set to smooth on the right. You can see that the motion is much more fluid, but it's still too smooth when the object hits the ground. There are no sharp or sudden movements, and this is because smooth tangents conform to the position of adjacent keyframes, which is useful for extremely fluid motions. The next interpolation type we will look at is flat, which just flattens the tangents. If we play back the animation, we can see that our object sort of hangs wherever we have keyframes. This is because flat tangents make the object slow down as it enters and leaves the keyframe. This results in a short pause while it goes through that keyframe. Flat tangents are good for more controlled, smooth animation. Linear interpolation is a very simple interpolation type. It just sets the tangents to create a straight line between keyframes. This type is good for mechanical movements because the animation is steady. It doesn't speed up or slow down. The last common tangent type is stepped. Changing the tangents to stepped really changes the look of our F-curve in the graph editor. When we play back the animation, we can see our object isn't smoothly animated, but instead stays in one place until the next keyframe. This type is good to have as the default type for your keyframes when you begin a very complex animation. This way you can focus on the timing of your animation without the distraction of the interpolation. You will probably need a mix of interpolation types throughout your animation. In this lesson, we're going to learn how cycling can be used to animate more efficiently. Here we have an oscillating fan. We need to animate both the side-to-side motion and the rotation of the fan blade. We will begin with the side-to-side movement. To start, let's just set a keyframe at the current rotation. Then we'll change the time, rotate the fan to the other side, and keyframe it. Now all we have to do is move the time forward again and copy the first keyframe. Now we can see that the fan moves side to side once. We could continue just copy-pasting the keyframes, but a faster solution would be to turn on cycling. What cycling does is it repeats your animation forever, saving you time from having to hand key all of the repetitions. Alright, now that we have the fan moving correctly, let's animate the fan blade. We can do this with just two keyframes, a keyframe on frame 1 and a keyframe at a later time of the fan blade rotated. Let's play this back. You'll notice that the side-to-side movement looks good, but the fan only spins once. Now we can turn on cycling with offset. And what this does is it looks at the last keyframe and then continues cycling from that value. So our fan rotates at a steady pace for however long our animation is. We can edit how fast the fan blade turns by dragging the second keyframe on the time slider. The closer they are together, the faster it rotates. Our fan animation is complete, so let's look at a more complicated example, a walk cycle. Creating a walk is a complicated task, requiring a lot of keyframes and tweaking. So an industry standard practice is only animating 2 steps of the walk and then cycling it. Here we can see the small part of the walk we have animated. Now if we turn on cycling, we can see our character walk smoothly, saving us lots of time and effort. In this lesson, we will learn about camera animation and motion paths. A camera in 3D is similar to a camera in real life. You look at your scene through it. When you watch your animation, you are seeing it through a camera. Let's look at a quick animation of a camera rotating around our little friend Roscoe. Here is what the camera sees. The camera is important to remember while you are animating, because you don't want all of your action to be out of sight or covered up by something else. You can animate a camera just like you would any other object, by keying its attributes. One way to quickly animate our camera, or any object for that matter, is with a motion path. To make one, we just need an object and a 3D curve to use as the path. Now, if we take a look at the camera view again, you will see the camera is attached to the curve. Another example of using a motion path is a sled moving down a hill. We can just draw the path on the hill and attach it to the sled. Now our sled is animated moving down the hill. The motion path uses the current time slider range as a start and end of the animation, but we can edit that to make the sled move faster or slower. As we saw in this lesson, it's important to know how to animate a camera and what the camera sees in the scene. We also learned how to use motion paths to quickly animate an object along a curve. In this lesson, we will learn about rigging. Now, rigging is the process of creating connections between objects to make animating easier. Now, it can be a very complicated process, such as creating controls for a human character, or it can be as simple as telling one object to follow another object. While rigging is not animating in the strictest sense, knowing the basics will help you animate more efficiently. Here we have our character's hand. If we try to animate this without a rig, it would be almost impossible. We would have to animate small parts of the hand and keyframe the rotation and translation. Then move on to the next part of the finger and continue the process. Or we can take some time before animating to create a rig and then make our life much easier. Now once this rig is built, we can simply change an attribute to make our hand close. This rig is constructed of many different pieces, which we'll learn about in the following lessons. One common and powerful rigging tool is parenting. Let's take a look at an example. We have our character running around in circles, but we want to control him with another character. By parenting our runner to this new character, we create a parent-child relationship. The child can move freely, but if the parent moves, the child will move with it. As you can see, our character is still running around after being parented, but if we move the parent, then the child also moves. The child can be independently animated, but it will also inherit transform data from the parent. So, if we scale the parent, the child also scales. But if we scale the child, the parent does not change. All rigs have control objects, and ours is no different. The parent is controlling the child, so we call it the control object. Now, most rigs are built so that you can only animate based off the control objects. In the following lessons, we'll learn about the various tools used to create a rig. In this lesson, we will learn about constraints. Earlier, we learned how to attach a camera to a motion path to make it move along a curve. Now, this is done by using a path constraint. But what are constraints? Well, constraints limit an object's position, rotation, or scale based off of various attributes of the control object. Let's take a look at an example, the target constraint. Here we have our character with something flying around in front of his face. Our goal is to animate his eyes to follow that flying object. Let's try to animate this by just keyframing the rotation. So we'll grab an eye, rotate it until we think it's pointing at that object, then grab the other eye, do the same. We just started and we already got a little problem. He looks cross-eyed. We can fix that by rotating the eye again. Now, this may take some time. This would be much easier to animate using a target constraint. So let's create a target constraint with the fly as the control object and the eyes, which are the ones being constrained. Now, when we play back the animation, we can see that his eyes follow the fly wherever it goes. This is a great time saver. We can even animate this constraint turning on and off. So his eyes can be wandering until they lock onto the fly. The target constraint creates an indirect connection between attributes, the fly's position, which is driving the eye's rotation. So as we saw, constraints connect an object's attributes together. A great feature of constraints is that we can animate them on and off. Now this lets us use multiple constraints on the same object and use keyframes and constraints together. Now, constraints are a helpful rigging tool used to restrict unnecessary movements, and this makes animating easier. In this lesson, we'll learn